Good evening, everyone. Thank you for coming, and welcome to Caltech. My name is Anna Ho, and I'm a graduate student here in the Astronomy department. Tonight, as always, we're going to start with a 30-minute lecture, followed by events in two different spaces. In here, we'll have a 90-minute Q&A panel with some astronomers, and you can ask them questions you have about subject matter related to the lecture, or basically anything you want, things you've always been wondering about astronomy. We're also going to have telescope viewing in the fields outside. So to get there, you'll exit the door you came in, you'll take a right, and then you'll take the first right, basically walk on the outside of this wall, and you'll see the fields on your right. The telescope captain told me that the weather looks great, and the plan is to observe Albireo, which is a star system you're going to hear about in Erik's talk tonight. You'll get to observe Mars, Saturn, and the Moon. So that's the plan. Oh, right, I'm supposed to remind you that when you go to the telescopes, you are not allowed to bring certain things to the field. No food, no drinks, no smoking, no pets, and no high heels, because high heels can damage the turf, and if we do that, we might not be allowed to use the fields again. So please don't wear high heels. If you get lost or you have any questions at any time during the evening, you can identify volunteers by these badges. And finally, if you saw outside, that we have a schedule of our events coming up. So the next lecture is in this room on October 12th at 8 p.m. And that's called Ceres, an unexpectedly active dwarf planet. It's about findings from the Dawn mission. So with that, it's my great pleasure to introduce my friend and colleague, Erik Petigura. Erik does research on exoplanets, which are planets in solar systems that are not our own, elsewhere in the galaxy. But tonight he's going to be talking about something different. He's going to talk about cosmic cartography, a billion stars in 6 dimensions, and the Gaia revolution. And a fun fact, when Erik was 5 years old, for Halloween he dressed up as this 16th century astronomer named Tycho Brahe. And, and here he is tonight, and Tycho Brahe will actually make an appearance in his talk. So it all came full circle.
Thanks. All right, so show of hands who also dressed up as Tycho. Okay, just me. Everyone thought I was a pirate. Thank you so much for coming here on a Friday night. It's delightful to see all of these eager faces, especially all of the young faces here. So I hope to tell you some interesting things about our galaxy and the universe. Okay, so I want to motivate the title, Cosmic Cartography. So cartography, as many of you know, is the science of making maps. So this is a map by Abraham Ortelius from 1570, and it's the first modern map of the world. And it is a crowning achievement of 15th and 16th century European exploration. So the general picture is right, but you can see the New World looks a little weird. Antarctica was way too big. And what this is meant to show is that human beings have been making maps for hundreds of years. And in that same vein, we've also been making maps of the sky for thousands of years. And so cosmic cartography, sometimes known as astrometry, which is Greek for measuring the stars, is something we've been doing for a long time. And by measuring the stars, we learn about the universe and our place within it. Okay, so now returning to the analogy of a map. When we think about how good a map is, how detailed it is, we want to think about two quantities. One is how detailed is the map? How many features are on the map? This could be things like rivers, mountains, towns, that sort of thing. And the other thing we want to think about is the precision of the map. How accurately are the places, the features that are labeled, represented on that map? So how does Ortelius' map stack up? Well, there's about 1,000 features on this map. And you can see Europe is pretty good. That's because this was made by a European. But if you look at the New World, there's some sort of weird shapes going on. And that's because our knowledge or Abraham's knowledge of the New World was not that good at the time. So when we think about the precision of this map, it's tens to hundreds of kilometers. And another way to think about precision on the surface of a sphere, the Earth is a sphere, any flat earthers may leave now. And you can also measure this in terms of angles. So the Earth has a 24,000 kilometer circumference, and so an error, a precision of 100 to 1,000 kilometers corresponds to about 1 to 10 degrees. So not bad for the 16th century. But if you compare this to a modern map, which is constructed with the aid of satellites and GPS, we're doing much better today. So a modern map has several hundreds of trillions of features. And you can access a map like this anytime you look at Google Maps. And our precision is much better as well. We know the location of rivers, every bend in the river on the Earth, to a precision of about a meter. And so if you think in terms of degrees, that corresponds to 10 millionths of a degree, 10 micro degrees. That's a very small angle. And so when astronomers talk about small angles, we use another unit, which we call an arcsecond. So this is 4/100ths of an arcsecond. And I want to give you sort of an appreciation for these angles. So everyone's familiar with a degree, and I want to give you all the ultimate rule of thumb. So everyone take your thumb out and put it at arm's length. Look at it with one eye. The size of your thumbnail is about a square degree. Your thumb is about 1 degree by 1 degree. The moon, as a point of reference, is about 1/2 degree by 1/2 degree. And so, to quote the famous astronomer Nicholas Sparks, wherever you are in the world, the moon is never bigger than your thumb. And that doesn't matter if the moon is down by the horizon and looks all romantic, or if the internet is wigging out about a supermoon, you can always cover the moon with your thumb because the moon is only 1/2 degree. Okay, but we have units for smaller angles as well. So an arc minute is 1/60th of a degree. That's the size of your thumb at the distance of a football field. So it's a much smaller angle. And an arc second is 1/60th of an arc minute. That's the size of your thumb at the distance halfway to downtown LA. So a very small unit of angle. Okay. So how do we talk about features on a map? Well, you may have heard of terms like latitude and longitude, and that's what we use to label positions on the Earth. So in Pasadena, we're at 34 degrees north and 118 degrees west. Now, what does this mean? Well, we live on a sphere that rotates. And on a sphere that rotates, there are 2 special points on that sphere, the north and the south pole. And so one of those coordinates has a very intuitive definition. It's just the angle you are off the equator. The equator, of course, is the line between the north and the south pole. So to get to Pasadena, we go 34 degrees up from the equator. But what about longitude? Longitude tells you how far east or west you are. But if you think about it, there's no obvious way to divide the Earth up into east and west. And so this is just a matter of convention. And we've decided that 0 degrees longitude runs on a line that connects the North Pole to Greenwich, England, for some reason, down to the South Pole. And so 0, 0, the origin of the Earth's coordinate system, is this fairly unremarkable part of ocean off the coast of Africa. So to get to Pasadena, we start here, we go up by 34 degrees, and we go west by 118 degrees. Now, you can also think of the sky as a sphere as well. So here's an image of the sky projected onto the flat screen. And of course, there's always issues when you project round things onto flat things. If you look closely and you know your constellations, you might recognize a few. Here's Orion, the hunter, your cat. Here's Ursa Major, and the Big Dipper. And finally, one of my favorites, Cygnus the Swan. So how do we talk about the positions of stars? Well, the sky we can think of as a sphere, so we can use those same ideas, latitude and longitude. And just like there's a special point on the Earth, there's a special point on the sky. And that's the point directly above the North Pole. So if you go out and you take a long picture of the sky, you'll see all of the stars rotate around a single point. Now, there happens to be a star there, but that's sort of by chance. There's no fundamental reason why there needs to be a star there. There just happens to be a star that's very near the celestial North Pole. So when we talk about north and south, we're talking about how far we are from the celestial equator up to the North Pole. Okay, so let's talk about finding the position of a star on the sky. Now, latitude has a very intuitive definition, the distance you are from the celestial equator. Longitude is a little tricky. It's a little bit more arbitrary. It depends on a definition. And we've defined zero longitude to be a point called the vernal equinox. You can ask me about this later. So how do we find the position of a star? Well, as Anna mentioned, Albireo is one of my favorite stars. It's actually not one star. It's two stars that are orbiting one another. And one of the reasons why I like this star is there are different temperatures. This blue star is much hotter than this red star down here. In astronomy, color often is a clue to the temperature of an object. Also, I went to Berkeley, and so this is kind of nice too. Okay, so how do we find Albireo? Well, just like Pasadena has a latitude and longitude, Albireo has a longitude and a latitude. In astronomy, we have weird names for everything, and so we call the longitude the right ascension, and we call the latitude the declination. That's not important. You can forget that if you need to. Okay, so Albireo, to find that, we go over in longitude almost all the way around the celestial sphere, 293 degrees, and we go up 28 degrees, and there it is. So mapping the stars, mapping the sky, just involves measuring the latitudes and longitudes of as many stars as you want. Okay, who's been to Griffith Park? Great. Griffith Park is amazing. Griffith Observatory is one of my favorite places. Next time you go, pause right before you get into the observatory. There's this cool monument out in front that has sort of the weighty name of the monument of the astronomers. And there are these tall figures depicted here. And I want to talk about a few of them in this talk. So one of them depicted is this rather stern-looking gentleman. This is Hipparcos. He was a Greek who lived over 2,000 years ago. And Hipparcos was a physicist, a mathematician, but he was also an astronomer. And among other things, he created a map of all of the stars he could see in the night sky. So if you go out into a dark sky, you can see about 1,000 stars. And Hipparcos tried to measure the latitude and longitude of all of those stars. Now, this is one of the most important books, the most important pieces of data ever compiled by our species. It was later bound up in a book by a guy named Ptolemy. And I'm showing a picture of it. But you might notice that there's something unexpected about this table of stellar positions. So the columns are all in Arabic. And I think this underscores just how important this catalog, this table of stars were. And in fact, if it wasn't for Arab scholars that translated Ptolemy's work, who in turn copied Hipparchus' work, we would have lost this catalog. So the story is kind of interesting. Over 2,000 years ago, Hipparchus compiles the star catalog. 300 years later, Ptolemy sort of copies it and says that he measured these stars himself. So this is one of the earliest cases of scientific fraud. Around the 800s, Arab scholars translated the Greek into Arabic. It's something called Al-Majesty, which is where we get this Amalgist name in English from. And then in the 1200s, Spanish scholars in Granada translated it back from Arabic. So Ptolemy cataloged the positions of the stars, and what he noticed by comparing his catalog to previous catalogs is that the North Star isn't fixed in the sky. The North Star actually moves. And this is due to the fact that the spin axis of the Earth is not constant. It wobbles. If you've ever played with a top, you'll notice that the axis of the top or the gyroscope precesses, and the same thing is true for the Earth. The Earth is not a perfect sphere. The sun exerts tides on the Earth, and that causes the Earth to precess. So this is a remarkable achievement for over 2,000 years ago. Hipparchus realized that the axis of the Earth was not fixed. And if you look at this table, this diagram, what this shows is the position of the celestial North Pole as a function of the calendar year. So right now, we're in the year 2000, about, and there happens to be a bright star that's right above the celestial North Pole. But in Hipparcos' day, there was no bright star there. And in fact, you see that we live in kind of an interesting time where there happens to be a relatively bright star near the celestial North Pole. Coincidence. In about 14,000 years, Vega will be sort of near the celestial North Pole, so you can wait around for that. All right. So a remarkable achievement for 2,000 years ago. Let's return to Griffith Park and let's look at some of these other astronomers on there. Well, two other astronomers you'll see are Johannes Kepler and Isaac Newton. These two individuals made major contributions to our understanding of how the planets move in our solar system. But there's one individual who's left off, and that's Tycho Brahe, who played an equally important role. Now, it's impossible to talk about Tycho without talking about what a gangsta he was. So Tycho, when he was in college, got into a thing with another student. The dispute was over who was the better mathematician. Shade was thrown. Someone disrespected Tycho, and he did what anyone would do back in the day, which is he dueled him, right? So Tycho did that, and his opponent got the first step and took a very big chunk out of Tycho's nose, right? But that's no thing for this badass Dane. And so Tycho wore a gold nose in its place for the rest of his life. Okay, so Tycho measured latitudes and longitudes. Now, Tycho lived just before the invention of the telescope. So he was just using his naked eye. And because of that, he couldn't actually see any more stars than Hipparcos could 1,500 years ago. But he was obsessed with measuring their precision to ever greater and greater values. And so let me tell you about how he did that. He made some very interesting discoveries in terms of astronomical instrumentation. So remember that latitude is the easy coordinate to measure. To measure latitude, you basically just measure the distance between the North Pole and your favorite star. So you just measure that angle. But longitude is more complicated. Longitude, you actually can only measure relative between stars. So if you're trying to measure, if this is your, say, reference star, if this is your 0,0 star, and you're trying to measure the longitude over here, you have to measure an angle over a fairly large part of the sky. And remember that the stars are always moving, right? So as soon as you line up your protractor, your compass, or whatever, and you're trying to measure these two stars, the stars have moved. And so your measurements are off. So Gaia's later. Tycho's main contribution was that he realized that he could use a clock to measure angles much more precisely than a compass or a protractor. And so that's what's depicted here. What he did was to figure out the angle between this star and, say, that star. He just measured the difference in time that it took for this star to transit the meridian, which is just the line that connects the horizon and the North Star. And he used the Earth as a clock. So the Earth spins at a very constant rate, and so if you measure the difference in time between two stars crossing a line, you measure the difference in longitude. So clocks measure angles. Now, that's what's depicted here. Here you see Tycho selecting a star. One of his assistants is lining it up in a crosshairs. And then he seems like he has two children working for him. One of them is measuring the time that this star is crossing the meridian, and the other one is cataloging it in a table. Tycho was able to achieve much better measurements than Hipparcos could before him. So he measured the distance, the positions of around 1,000 stars, but he measured it to the precision of about 1 arc minute. An arc minute is an arc minute is about a 50th, 60th of a degree. That's 50 times better than Hipparcos could. And when he was making these precise measurements, there was something that started to bother him. the motion of Mars didn't quite look right. Mars was not following along the path that Tycho thought it should. And so here's a table in Latin of the position of Mars based on Tycho's measurements that were published by Johannes Kepler after his death. And no matter what Tycho did, he couldn't reconcile the observed positions of Mars with his data. And the reason was, it wasn't his data that was wrong, it was the model that was wrong. His model of the solar system, and indeed the universe, was wrong in a fundamental way. Tycho thought that the Earth was the center of the universe, the sun and all of the planets revolved around the Earth. And it took another astronomer, Johannes Kepler, to realize that you could fit the data much better if you put the sun at the center of the solar system, and you realized that the planets didn't move on perfect circles, as Tycho thought, but they moved on ellipses. And this realization was one of the main reasons that inspired Newton to come up with his universal law of gravitation. And so I think this illustrates a nice cycle that happens in science all the time, where someone comes up with a better technique of measurement, which has tension with existing models, which motivates, it necessitates the creation of better models, which eventually yields deeper understanding. Okay, so now I'd like to fast forward to the 20th century. So I've told you about Hipparcos and the precession of the equinoxes. I've told you about Tycho and Kepler and the elliptical orbits of the planets. But both of those astronomers got one fundamental thing wrong, which was that they assumed that the stars were infinitely far away and they were fixed, meaning that the stars did not move with respect to one another. We know now that that's not true. In fact, if you make observations of stars year after year, some stars appear to move rather noticeably against a background of other stars. So this is a star called Barnard's star. It's one of the nearest stars to the sun. And these frames in this image are taken 1 year apart from one another. So you can see this star moving against this background of other stars. Now, if you look at this data even more closely, you can see that it doesn't quite move in a straight line. It actually wobbles back and forth. Barnard's star is not wobbling. It's our vantage point on Barnard's star. This is an effect called parallax. Parallax is a long word for something that everyone understands at childhood. So again, take out your thumb, put it a few inches away from your face, and align your thumb such that you cover my face. Right? Block me out. All right? Close one eye. All right? Now open the other eye and close the first eye. Right? Hey, what's up? So what you've seen is that I've moved, right? So I'm a distant object, I'm a distant background star, and your thumb is some nearby star. And what you've seen by changing the vantage point very slightly, that your thumb appears to move relative to the background stars. This is why we have two eyes as opposed to one. Two eyes help us appreciate 3 dimensions. And that's exactly the technique that we use to measure the distances to the stars. So our Earth orbits the sun, thank you, Kepler. And when you look at a nearby star, what you see is that over the course of the Earth's orbit, it makes these circles relative against the background of more distant stars. And the farther away a star is, the smaller the circle it makes. And so by measuring these little loops, we can figure out how far away stars are. Now, of course, there's no such thing as a star at an infinite distance. And so if you actually do this, you need to measure all of the stars making their little loops. And in fact, stars have their own motion relative to the solar system. And so the combination of them making these loops and going in their own, we call it proper motion, causes these really cool corkscrews. That's how we measure the distance to stars. And this brings me to the final chapter in my talk, which is humanity's latest attempt to make detailed maps of the sky. So this is the Gaia mission by the European Space Agency. This mission is incredible in terms of its vision, its scope, and its accuracy. Gaia is measuring the positions of 1 billion stars to an insane level of precision, 10 microarcseconds. That's 3 billionths of a degree. And I want to give you an appreciation for how small that is. So remember, a degree is the size of your thumb at arm's length. 10 microarcseconds is the size of your thumb at the distance of the moon. So just let that sink in. In 2,000 years, we've gone from Hipparcos, measuring things kind of by eye, literally by eye, to measuring 1 billion objects at the precision of your thumb at the surface of the moon. It's remarkable. Gaia is maybe not what you think of when you think of a typical space telescope. Gaia actually has 2 telescopes mounted on this weird donut-shaped contraption. And the point of Gaia, the way in which Gaia makes these precision measurements is by being as stable as possible. So this donut is made out of an exotic material called silicon carbide, which is very resilient against thermal expansion and contraction, which would screw up the measurements. Just to give you a sense of scale, here are some technicians installing one of the mirrors of Gaia's telescope onto this silicon carbide donut. It's not possible to make measurements that are this precise from the ground. You need to go to space. And in fact, you can't just go into space, any old orbit. You got to go to a special place. So Hubble is in an orbit that we call low Earth orbit. It's only a few hundred miles above the surface of the Earth. And when you're that close to the Earth, you make very sort of rapid rotations around the Earth. And that's bad for precision measurements, because every time you come out of the shadow of the Earth, your telescope heats up, it expands, and it screws up your measurements. So Gaia is actually orbiting not around the Earth, but at a special point called the L2 Lagrange point. This is a special point in space where the gravity from the Earth and the Sun balance each other in a particular way, such that Gaia always orbits with the Earth and the Sun in the same part of the sky. And so Gaia can have a sun shield that blocks out the light from the star. And what you can see is that Gaia makes this really funky orbit specifically to avoid from passing behind the shadow of the Earth. Because if you pass around behind the shadow of the Earth, the temperature changes, and your optics change, and your measurement gets degraded. Gaia works by scanning 2 separate fields of the sky. The light from these distant stars comes in. It's focused by the telescope onto a massive array of CCD chips, so it's the same type of chip that you have in your camera. Gaia's CCD array has 1 billion pixels. So this is one of the largest cameras ever made, and it's the largest by far that's ever been flown in space. As Gaia scans the sky, these 2 different fields fall onto different parts of this CCD, and they drift across the CCD. And the fundamental thing that Gaia measures is the time at which a particular star crosses the middle of each CCD. And if this sounds familiar, it's exactly the same technique that Tycho used. Tycho was using mechanical clocks. Gaia uses atomic clocks. And even though these measurements are millions of times better than what Tycho was doing 400 years ago, I think if he was around today, he'd be very pleased to see that we're still using the same techniques that he pioneered even before the invention of the telescope. So in the last few minutes of my talk, I want to give you a sort of a flavor of some of the things that Gaia has taught us about our local corner of the galaxy and indeed the galaxy as a whole. So this is a visualization of Gaia Data Release 2, and it's sort of the first major release of Gaia. This occurred at April 25th this year, 2018, at noon Paris time. And I remember that because a colleague of mine, BJ Fulton, who's somewhere in the audience, we had the perfect paper to write using Gaia data. And so we both woke up at 3 a.m. California time in order to download the data when it was still hot off the presses and write a paper. And so what you can see is that all of these stars are moving, and you can see that the galaxy is a very dynamic place. Okay, so Gaia is helping us understand the properties of stars in our local solar neighborhood. So here's a map of the latitude and the longitude of different stars, and these stars are colored according to their actual color. You may notice that many of the stars are red. That's because the most common type of star is a red star. Well, we can do some cool things with this data. So we can sort this data based on its color. So we can put the blue stars on this part of the plot and the red stars on this part of the plot. And that tells us the temperature of these stars. And then with the Gaia data, we can also organize these stars based on their luminosity, because we have the distances to these stars. And we do that, what seems to be a disordered mess of stars actually collapses to this very interesting structure. This is a diagram called the Hertzsprung-Russell diagram. It's one of the most important plots in all of astronomy. And where a star lives on this dot tells you a lot about its composition, its properties, and its eventual fate. So the sun is a yellow dwarf star. It would maybe live around there. In 5 billion years, the sun will run out of fuel and evolve off the main sequence, which is this straight line here, and become a red giant star. And then when the sun finally dies, the core of the sun that remains will become a white dwarf. Gaia is also telling us about how our own galaxy was assembled. So we live in a spiral galaxy, and we think that spiral galaxies are formed by the successive mergers of smaller galaxies. So here's a computer simulation showing how we think spiral galaxies form. And what you can see is that as this central galaxy starts eating up smaller galaxies, it shreds them to pieces, and we call these sort of long tendrils tidal streams. This is one of the few things in astronomy where it actually helps to be a little bit farther away. So it's fairly easy to detect these in other galaxies. You can see the light from this disrupted galaxy as it's been torn apart by this larger galaxy. But these things are actually hard to see in our own galaxy because we're embedded within our galaxy, and the stars stretch over the entire sky. But because Gaia is an all-sky mission, we can actually identify these tidal streams in our own galaxy, and we can figure out what the Milky Way galaxy's last meal was. And then finally, Gaia is so precise that we can measure the properties of stars in other galaxies. So if you ever go to the southern hemisphere, go to a dark part of the sky, a dark place where you can look at the sky. And what you'll see are these two sort of wispy clouds that are off the plane of the Milky Way. These are the large and small Magellanic Clouds. These are satellite galaxies of the Milky Way. And these galaxies are about 150,000 light years from the Earth. And Gaia is so precise that we can actually measure the rotation of stars in these distant galaxies. So each one of these stars takes 250 million years to rotate around the galaxy, and Gaia is so precise that we can measure the small amount of that orbit. Okay, so to wrap up, the next time you go out into the night sky and look at the stars, think about how Hipparcos, back in ancient Greece, looked at the same stars that you're looking at today and realized that the axis of the Earth is not fixed. And then on a night like tonight, when Mars is out, think about how Tycho, Kepler, and Newton analyzed the positions of the planets and obsessed over getting the measurements just right, and realized how our planets move in our own solar system and our own place in the universe. And then finally, if you're really brave, try to count all the stars. You'll get to a number that's around 1,000. That's about as many stars as you can see with your naked eye. And when you get to that number, for each one of those stars that you counted, imagine 1,000 more stars. And then for each one of those stars, imagine 1,000 more stars. And think about how 1 million miles from the Earth, in the vacuum of space, there's a mission called Gaia that's slowly rotating and measuring the positions of all of them. Thank you. Okay. Let's see. Let's take 4 questions. All right. How about in the front?
What's the name of the star that's directly over the North Pole?
All right. Well, you already said part of it. So Polaris.
Oh, it's Polaris.
Yes. But it's kind of funny, right? Because we call it Polaris, even though it's not always going to be the North Star. So if we had lived 12,000 years ago, we might call Vega Polaris. It would be a different star. How about in the back?
When you showed that picture of that one star that was moving up and down, I think it started with the letter B.
Yeah.
What is the force of moving the star?
There's no force. So an object in motion stays in motion unless acted on by an external force. In space, there's nothing to slow that star down. And so the star, Barnard's star, has its own velocity. And it'll keep moving in that direction until passage of a nearby star or something perturbs it off that straight line. Okay. So, so the question was, in Gaia's model, how many free parameters are there? So Gaia is measuring the properties of 1 billion stars. Each of those stars has 6 astrometric parameters. And so Gaia is trying to solve for 6 billion unknowns, right? So that's a big problem. But Gaia actually makes 100 billion measurements. And so as you'll remember from linear algebra, if you have more measurements than you have unknowns, then you can solve it. Now, the way in which in which the team actually derives the astrometry, the final positions and velocities of the stars, is extremely challenging. In fact, the mission had to prove before they got the funding to actually build the mission, that they could actually muster the computational power to solve this giant system of equations. And it amounts to something like 10 to the 21 floating point operations. And they use supercomputers. There's no way that you could do this on your laptop. And in fact, the algorithmic complexity of the Gaia mission is astounding. So if any of you are computer science buffs, send me an email. I'll send you a paper. It's very cool. All right, one more question. In the front.
You mentioned you and your colleague were writing a paper based on data from Gaia. What's the paper about?
Yeah, so where's BJ? All right, so BJ is the lead author on that paper. So I should say his full name, BJ Fulton. So one of the things that BJ and I have worked on over the last couple of years, I promised people I wouldn't talk about exoplanets, but you forced me. I had no choice. So we study exoplanets, and we're very interested in the precise properties of exoplanets. How big are planets? Where are they located in their respective solar systems? We know of about 5,000 planets now outside of the solar system, and the most prolific mission is the Kepler mission. For the longest time, we didn't have very good sizes of stars that Kepler observed. And that's a big problem because you only understand your planet to the extent you understand your star. And so our uncertainty in the size of the stars was rather large. But what BJ and I did was use Gaia to measure the precise sizes of these stars. And in doing so, we could measure much more precisely the sizes of the planets and look for interesting features in the population of planets. And what we found was that small planets, planets between the size of the Earth and Neptune, actually come in sort of 2 flavors. One flavor of planet is between about twice the size of the Earth and 3 times the size of the Earth. And the other class of planets is about 1 to maybe 1.5 times the size of the Earth. And there's a gap in the middle that distribution. And I'm proud to say that that gap is known as the Fulton Gap, named after my colleague in the audience. And so that's the paper we were interested in publishing, and that's why I set my alarm for 3 in the morning.
All right, let's thank Erik again. Okay, we're going to get started with the Q&A. So I'll let the panelists introduce themselves, and then you can ask whatever you want.
Hello, everyone. Thanks for coming. I'm Michael. I'm a third-year graduate student.
Just in case.
And I work mostly on exoplanets.
No, I did. That's not the kind of thing.
Hello, I'm Denise. I'm a fifth-year graduate student here, and I work on cosmology, which is a fancy word for studying the properties of the universe.
Hey everyone, I'm Dylan, and I'm a newly minted third-year grad student, and I study the radio afterglows of various different kinds of explosions.
My name is Mia. I just finished my first year and passed my qualifying exams. I will take my round of applause now. Oh, yeah, thanks. Okay. And I do galactic archaeology. So please ask me any questions about galaxies. I love galaxies. Cool. So, are there any questions? I guess we'll start. Yes.
Well, first, I'd like to thank you. We have all these people who are interested in astronomy. How often do you expect we ever get a chance to sit down with some astronomers and ask questions?
Thank you. Well, thank you for coming. I appreciate that.
Now, a question.
Okay.
I guess it's about isotropy. So, if you look at a large scale, any direction you look in the universe is going to look roughly the same. If the universe is 13.8 billion years old, so we go to a planet around a star 13.8 billion light years away. If we look up, is it still isotropic? Is it only isotropic in that direction? What's going to be on the other side, the edge of the universe?
So the question was about isotropy, which is this idea that the universe looks the same in all directions. So the question was, if we go to the edge of the observable universe, will things still be isotropic? And I will turn this over to our resident cosmology expert, Denise.
Well, so I guess technically the answer to that question is we don't really know. But in theory, if you were to talk to some aliens living on a planet, 13 billion light years away, the answer should be yes, they would also observe isotropy in the universe. It would also be, for them, it would be the same in every direction. But we can't really say for sure because that's as far as we can observe. And so the technical answer is we don't really know.
Just to add on a little bit to what Denise was saying, a pithy way of talking about isotropy is that the universe has no center. There's no special point in the universe. And so there's this great T-shirt that I've seen, but I do not personally own, that says, I've been to the center of the universe, and so have you. Okay, second question. Yeah. Oh, actually, we have a question here.
So I know someone once who's an astrobiologist, and I asked the question, so how close do you think we are to actually discovering intelligent life in the universe? And he was rather flippant and said, oh, we already have. So I was just wondering if any of you would weigh in on your thoughts and what you've seen in your research.
Okay. So the question is, how close do we think we are to finding aliens of some kind? Some sort of intelligent life? Maybe Michael would like to take this?
Well, okay. So obviously that's a question that a lot of people are really interested in. So, people have done calculations, but the problem is the calculations depend on several parameters, and none of which we know to any degree of certainty. So, for example, if you have a normal planet like the Earth, and let's make it almost exactly like the Earth, right? Same size, same mass, same temperature, same star, how likely is it for life to arise, right? And the answer could be anywhere from nearly 0 to 100%. And we basically have no idea where it is in that range, because we don't have a planet like the Earth in our solar system that we can go to and to see whether there's life on it. So there are people who are trying to discover intelligent aliens. Basically, the only way we know how is to listen for radio signals, and that's what Breakthrough Listen is supposed to do. This is an initiative that's funded by billionaires, and the goal is to detect a planet like the Earth with a civilization like our civilization. So essentially, a civilization that emits the same amount of radio waves as we do should be detectable if they live, among the closest stars to us. If you ask them, they'll detect something within the next 10 years. But, they would say that. So, yeah, basically we don't know.
All right, so that's 2 out of 2 questions we don't know. We have a great track record going. Does anyone else want to ask a question? Yes, back there?
It's a two-part question. One is why, for any of the panelists, why did you choose your field of study? And what advice would you give to a high school student who is interested in studying astronomy?
All right, great question. So it's a 2-part question. The first part is, how did we panelists decide on our career or our field of study? And the second part is, what advice might we have for students, high school students or other students, who might be interested in doing something similar? So I haven't had time to formulate a response, so we're going to start at the other end.
Okay. Well, okay. I still don't know that I'm going to be an astronomer in the future, so maybe I shouldn't be the one to start.
I can start if you want.
Oh no, it's okay. But essentially, I've always been interested in astronomy. When I was small, I had a small telescope, so I would look at the galaxies, the star clusters, the planets, and I would follow the astronomy news. And in university, I just tried to take as many courses as I can in different topics, because I still didn't know what I wanted to do. And I really liked the astronomy classes I took, because they were well taught, and there were many research opportunities in astronomy, because the sky is big. Right, you can always find your niche. And the number of astronomers in the world is something like 10,000, right? It's not that big. And after university, well, I actually didn't go directly to graduate school. I went to industry. But after 2 years, I was like, well, you know what? I want to do some more astronomy research. So here I am.
I would say I started getting interested in astronomy when I was in high school. I had always been kind of interested in math and science in general, and then high school was kind of a time when I started reading books on astronomy, and I thought it was really cool and interesting, and I didn't know much about the subject, but I wanted to know more. And so then I decided to study physics in college, and then I started, taking astronomy classes, and then eventually I ended up deciding that that was going to be my path of study. So yeah, that's my story. What advice would I have for a high school student that's interested in astronomy? Stay curious. Always try to learn new things. And for more practical advice, study hard in your math classes.
Yeah, so I distinctly remember going on a visit, one of the prospective visits for prospective graduate students. And the person who did the intro meeting asked, so who here is wanted to be an astronomer ever since they're little? And everybody raised their hand except for me. I hated science when I was little. I thought it was super boring. I was okay at math. But then at some point, I remember I decided to go to the summer camp. And it was in the middle of a national forest in North Carolina. North Carolina, he is from North Carolina. And it was the first time that I'd seen the dark sky, a sky so dark where you could just see, the smearing of light that's the Milky Way. And I remember I just went out in the middle of this forest road at midnight, and I just lay down and I looked at the sky for 2 hours. And I think that was definitely one of the formative experiences for me that led me to become an astronomer. I wasn't really decided then. One huge thing for me was that I had a really, really good astronomy professor. I went to Pomona College, about 25 miles from here in Claremont. And Phil Choi, I don't know if any of you have met him. He's fantastic. He basically just took me under his wing, and he was like, oh, you know, there are like some research opportunities in Pasadena. Why don't you apply for one of these? And so I was like, okay, I guess I will. And I guess I got one of them, and I sort of just stuck with it ever since.
Cool. So we don't have all the small children. Oh, just kidding. No, there's one small child. Never mind. My answer is that space is cool as something that's really cool and definitely not a curse word or anything. It's really cool. Space is cool, and that's why I got into it. My advice would be that if there's one thing that a lot of people say about astronomy that is patently false, is that you have to be a genius to do it. This is false because I am doing astronomy. But also because in general, you don't actually have to be like innately intelligent. No one up here, I don't think, would say that they are, you know, a genius. Well, I don't know. Maybe some people up here would say they're a genius. But I think the most successful astronomers that I know, although they are smart, a lot of them weren't, you know, born that way. They worked really hard. They cared a lot about what they studied. And I think that's a lot more important than, you know, being immediately good at physics or math or anything. Although it does help to do physics or math, if that's what you're interested in.
Just one little bit of practical advice. One of the most important skills, if you're interested in doing astronomy, is actually knowing how to program computers. And so that's something that I would definitely focus on in college, or maybe even in high school if you get the chance, if you're interested in that.
Yeah, so the side benefit of that is even if you don't want to do astronomy, there's a ton of other stuff you can do. Right? There's a lot of industry jobs, there's other research positions, there's like a ton of jobs that require programming these days.
Each of you have your own specialties of what you really like. Could each of you tell us briefly what you find so fascinating about your individual likes?
Okay. All right, sure. So the question is, all of us have our own specialties. Can you please tell us what you find so fascinating about your own specialty? Yeah, so right now I mostly study exoplanets. So these are planets around stars other than the sun, right? So the sun has 8 planets, but we discovered thousands and thousands of planets around other stars. And actually the Gaia mission that you heard about today, in a few years or so, they're going to discover 20,000 exoplanets, at least. Right? So there's a flood of data coming in. And what I find so interesting about exoplanets is that these are worlds like our own. Right? You can imagine going there for a visit. You can imagine setting a foot on them, at least, you know, the rocky ones. And we're edging closer and closer to being able to probe these planets for evidence of life. Right, so that's hard because we think that life can only originate on small rocky planets, and small planets are very hard to detect and even harder to characterize. But we're making progress. We're making progress in analyzing the atmospheres of these planets to see what they're made out of. And we are making progress in getting statistics for these planets, like how often they form and what sizes they are, and how many of them have the potential for life.
So my specialty is cosmology, and the way that I like to describe cosmology is everything that's bigger than a galaxy. And I think the thing that I find so fascinating about cosmology is that it's sort of a way to study the most fundamental physics of the universe and the most fundamental questions about how everything got here. Cosmology encompasses the study of things that happened 13 billion years ago, all the way to today. The study of the large-scale structure that the Milky Way and other galaxies are embedded in, and the structure that shaped the history of the Milky Way galaxy itself. And so I think that it's a way of asking questions that are quite literally the biggest questions in the universe, and I think that it's really cool to get us closer to understanding where we came from, not just us here on Earth, but where it all came from.
So I study explosions, as I mentioned earlier, and I find explosions fascinating because, things go boom. But a little less flippantly, I think that one really cool direction that astronomy is taking is this movement into the fourth dimension, right? So when Hipparcos looked up in the sky, he saw stars in 2 dimensions. We have latitude and longitude. What Gaia is giving us is distances to stars, and that's the 3rd dimension. But now we're looking into how things change with time. And the more sorts of ways that you can look at the universe that are unique from what's been done before, the more you can learn about physics and how the universe works.
I study galaxies with 3 exclamation points, as you can see. And in particular, I do something called Galactic Archaeology, which is really similar to archaeology here on Earth. The idea behind archaeology here on Earth is you look into the past by looking at what previous cultures have left behind. And the same is true for galactic archaeology. So what we're trying to do is look into the past of galaxies by looking at what previous stars have left behind. So I think that's really interesting for a lot of reasons. One, because deep down I really wanted to be a paleontologist and study dinosaurs. And 2, because it's really interesting. You can, like Dylan said, it's really cool that we can actually see into the past and see what happened to these galaxies. And in particular, look at galaxies that probably built up to form galaxies like our Milky Way today. So that's also, to me, that also touches on the question of, where did it come from? Where did we come from? And then finally, I think one thing that's really interesting is that, again, as Dylan mentioned, we can now start to think of galaxies as evolving systems, because now we have the ability to see how the stars in our own galaxies are moving over time. The galaxy isn't just a static thing, right? It's really easy. You look at a picture in a textbook and you sort of see this blob of stars. But a galaxy is more than that, right? It's a changing system over time. And looking at the ways that things interact with each other in a galaxy, the ways that different galaxies interact with each other, to me that's really exciting. Cool. Yeah, one question back there?
We heard, if I understood correctly, that the universe has no center. If in fact things started with a Big Bang and some small mass, wouldn't that indicate a place from which everything emanated, same speed, same direction, which would be the center?
So to repeat the question was, if the universe has no center, then how could there have been a Big Bang from which everything originated? Is that?
Well, wouldn't it indicate that would be the center?
Right, wouldn't it indicate that where it started, that would be the center of the universe? So Denise will once again take this question.
So that's a really great question. The answer to that is that everything is expanding in the universe, and that's true not just of all the matter in the universe, the galaxies and the gas and the stars and everything, but also the fabric of space-time itself is expanding. And so when we look back and talk about the Big Bang, the Big Bang was the origin of not just the matter in the universe, but also of space-time itself. And so we call that a singularity, meaning that all of space-time was compressed into a single point at the Big Bang and began to expand outward at the point that the Big Bang happened. And so what that means is that the Big Bang didn't have a location because there was no such thing as location at that time. All locations were compressed into one point and then began to expand outward. Does that make sense? It's hard to wrap your head around these things, even for me, and I've been studying this for years.
Yeah, so a classic analogy, which is actually wrong in many ways that Denise could probably explain, I perhaps couldn't, is that imagine instead of living in 3 dimensions, we actually lived in 2 dimensions. And imagine that 2 dimensions was on the surface of a balloon. Like galaxies are just little polka dots on the balloon. And imagine that the balloon is being blown up. Right? There is a center of the balloon. It's sort of the middle, but that's not in our universe, right? It's some other dimension that doesn't exist in our universe. There's no actual point on the balloon that's the center of the balloon itself. And so that's one way to think about how there's no center in the universe.
Yeah, I think it's probably for Denise. When I was a kid, there was this ideal of the oscillating universe. The idea that the universe might stop expanding and start contracting, and then it might keep going, expanding, contracting, sorry. It might keep doing this, for who knows how long, and who knows how long it's done it, before. How much, it seems to me that theory's kind of fallen by the wayside. How much has it fallen by the wayside? Have cosmologists kind of given up on the oscillating universe theory, or did they still think it might be possible? And how does dark matter fit into the oscillating universe theory, or dark energy?
That's a great question, right? So the question is, there was this theory about an oscillating universe where at some point the universe would stop expanding and start contracting, and then maybe have another Big Bang and start expanding again, potentially forever. And is this still a viable theory? So the answer is actually, in the last couple of decades, we've gotten much, much better data on the universe and on the expansion of the universe. And what we've determined is it does not look like that's going to happen. The reason for this is so we can actually measure the speed at which galaxies are expanding away from each other, and we can calculate using our theoretical models whether they will continue to expand forever or whether they will eventually stop and turn around. And what we believe now is that from these newer measurements is that it looks like they will continue to expand forever. This theory, if it seems as though this theory has fallen by the wayside, it's because we have better data now that seems to rule out that model. Yeah. And the second part of your question is, how does dark matter and dark energy fit into this, which is also a really great question. So dark matter and dark energy fit into this physical model that we have for how the universe will continue to evolve in time. So in Einstein's theory of general relativity, it's a theory of gravity, and so the total amount of matter and energy in the universe actually determines how the space-time in the universe will evolve over time. And so if we measure the amount of dark matter and dark energy that exist in the universe, which is something that we are doing now to better and better precision, we can refine our model and use these equations to determine how the universe will continue to evolve.
Can I sneak in a question about dark matter?
Of course.
We don't seem to know what it is. It's just a big placeholder. But it's always, at least from what I've heard and read, it's always spoken of like dark matter's out there. Is it possible that it could be here, but we don't know? We don't know how to measure it. We're too stupid to know that it's here. You understand what I'm saying?
Right. So dark matter is here. There's dark matter in the Milky Way. It is all around us.
All around us?
Yes.
Like in this room?
Yes.
Oh, okay.
Yes. Yes, it's all around us in this room, yes. There's different concentrations of dark matter in different places. So there's a greater density of dark matter in the center of the Milky Way. than there is here, a little bit farther out from the center. But it is everywhere.
And if it is everywhere, are we making any progress to figuring out what it is?
Right. Oh, right. So the question is, are we making any progress toward figuring out what dark matter is? So the answer is there are lots of very smart people working on trying to figure out what dark matter is. So that's more of a particle physics specialty, actually. So there are a number of experiments that are trying to actually directly detect dark matter particles. There's an experiment called ADMX. There's an experiment I think called Xenon. Then there's probably other experiments too that I'm forgetting the name of. But yes, there are basically several different groups of people working on basically experiments to try and detect different types of particles that we think might make up dark matter.
Thank you.
Yeah. Yes. Oh, well, here, let's see if someone that has not yet asked a question has one. Yes. That's a great question. Yes. So the question is, the universe has been expanding since the Big Bang. Has it changed? Has that expansion changed speed at all? The answer is yes. So actually, the Nobel Prize in Physics in 2011 was awarded to some people who discovered that expansion is actually accelerating in time. Yeah, so the universe is actually expanding faster now than it was in the past. And that is one of the big pieces of evidence that we have for the existence of dark energy. Yeah, so I mentioned before Einstein's equations govern how the universe evolves in time. So the reason that we know of the existence of dark energy is because the way that fits into that equation, it causes the acceleration of that expansion of the universe, and that is something that we have observed.
Yeah, so just to tie it into your question from before, this is one of the big pieces of observational evidence that we have that the universe isn't going to fall back in. Because if it were falling back in, you'd expect that it would be decelerating instead of accelerating. Yeah.
Is there any even a hypothesis of what dark energy is? Because it's kind of almost like dark energy and matter are just two things that we just can't detect or see or feel. And I just not heard enough about what maybe would be causing or the makeup of dark energy.
Right. So, by the way, if any of you, sorry, I feel like I'm kind of monopolizing these questions, so if any of you guys want to take some of the cosmology questions, feel free. Okay, so the question is, are there theories for what dark energy is? There are. We don't currently know if any of them are right, but there are a couple of theories. So stop me if this gets too technical. One theory, in quantum mechanics, there's a theory that of something called vacuum energy, and what that means is that space itself would have some kind of inherent energy density in it. And we don't know for sure if this accounts for dark energy, and there are a number of problems with that theory, such as the fact that when we try to calculate, we get a number that's wildly wrong. But potentially, if we manage to work out the issues with this theory, it could be the case that that dark energy is due to this quantum mechanical vacuum energy density. Another theory for dark energy is something called modified gravity, and what that would be is the idea is that perhaps we don't have a complete understanding of how gravity works, and so we would have to make some modifications to Einstein's equations of general relativity. which would not be, you know, general relativity was itself some modifications to Newton's law of gravity. So it's possible that the equations we have are not quite right and we need to modify them in order to correctly describe what's happening. So that's another possibility for where dark energy is coming from. Or it could be something that's different from both of those. We don't really know. Dark energy is, you know, the biggest mystery in cosmology today. So it's kind of an exciting time. We're still trying to figure it out.
What rate are we expanding? Is there a rate?
There is a rate. Yes.
A rate?
Yes.
Okay. And how do you measure that then? And how do you determine it's fast or slow or whatever? How do you do that?
Right. So I'll repeat the question. The question is, at what rate is the universe expanding, and how do you measure it? I'm really sorry for monopolizing this. Do any of you guys want to take it? Okay.
Okay. So the question was, at what rate are we expanding? And that depends. So the way that we sort of write this down is we write the speed at which a galaxy at a given distance would be moving away from us. And you can, yeah. This is called Hubble's law, and it actually takes a very simple form, which Denise will write on the board. So we'll wait for Denise to write that. The velocity, v, is equal to this number, h, times the distance. And h has a value of about 70 kilometers per second per megaparsec. And so what that means is, so a parsec is about 3 light years, and a megaparsec is 1 million parsecs. So for a galaxy that is located at 3 million light years away from our galaxy, that galaxy, due to the expansion of the universe, would be moving away at 70 kilometers per second. The universe is very, very large. 1 megaparsec is barely anything on the scale of cosmology. And so when you start getting to really distant galaxies, they start flying away at incredible speeds. And you have to remember that these aren't actual speeds. The galaxy isn't actually sort of moving in the sense that you would normally think of motion. It's actually the space in between us that's expanding. And so the apparent motion is that speed. Yeah.
So another way to think about that is if you have a car on a road. The car is not, in this case, the car is a galaxy and the road is space itself. The car is not actually moving away from us. The road is stretching. So the car is moving farther and farther away at faster speeds. And the second question, how to measure it? Well, yes, I'm super excited about this question. Okay. So one way that we measure things is we need to know 2 things to measure what h is. We need to know the speeds and the distances. The speeds we can get by looking at the spectra of a galaxy. So the spectrum of a galaxy is if we take the light from the galaxy and split it into all the different colors that it makes. And it turns out that things moving away from us will have their spectrum shifted towards the red. This is called the red shift. It's kind of like the Doppler effect. So if you have for sound, right? If you have a police car that's moving towards you and moving away from you and it has its siren on, you can hear a change in pitch. It's sort of analogous to that, except with light. So things that are moving towards us will look blue, and things that are moving away from us will look relatively red compared to what they would look like normally. And so that's how we measure the v part, the velocity part. To measure the distances, we use something called standard candles. Well, there are lots of ways to measure distances, but one way, and the way that won the Nobel Prize in 2011, was using standard candles. So these are things that look the same brightness no matter what, or that are the same brightness no matter what. And so you can think of, if you have a candle close to you, it will look a lot brighter than a candle far away, even if they're the exact same kind of candle and the exact same brightness. So we use that to actually quantify distances and measure the d part. So what are standard candles? One thing that we can use is something called type 1a supernovae, which is a particular kind of stellar explosion. So if you have a star that is kind of like what our sun's corpse will eventually look like, sometimes you can get that star, it's called a white dwarf star, to explode. And that white dwarf, that explosion will we think can be standardized, so it can be treated like this standard candle, and that's one thing that we can use to measure the D part in this equation. And that's how we measure what H is. Cool. I've stunned them into silence. Okay, does that make sense? Did you have a follow-up question, or?
No.
Okay.
It's expanding our technology, keeping up with the expansion in the sense of the too simplistic. I mean, if it's expanding and then the matters and things are going out, does our technology is it keeping up with that action?
So the question is if our technology is keeping up with.
Right. When you say it's expanding, this means to me like it's getting further away or something.
Yes.
The equipment we have today, or the technology we have today, be able to stay in line with that?
So the expansion of the universe. So the question is if our technology will be able to keep up with the expansion of the universe. Yes. So the universe. Okay, I think maybe we've been a little glib here. So the expansion of the universe happens on really, really large scales. Things like our Milky Way, things like the Earth, will not expand because they're all gravitationally. Gravity is holding them together. Gravity is winning over the expansion of the universe. This only happens on really, really large scales where what we call dark energy might be taking over from gravity and causing this expansion. So for the most part, our technology on Earth doesn't have to change because Earth will not be affected by this expansion. So.
Right, so to give you some idea of how slow this expansion is, if you look at the H0 that's written on the board.
Yeah, here, I'll circle this for you.
Yeah, so that's the expansion rate of the universe, 20 kilometers per second per million light years. So if you have a galaxy that's a million light years away, then it's moving away from us at 20 kilometers per second. And that's about 10,000 times slower than the speed of light. So, yes, 10,000 times slower than the speed of light. So if you ask, wow, that galaxy that's 1 million light years away, how long does it take to travel another million light years? It's going to be 10,000 times 1 million years. So that's the time scale on which the expansion happens. Another way you can think about it is the universe is about 14 billion years old. So that's kind of the scale that we had to be worried about the expansion.
Yeah, so I just wrote on the board a scale. So the units of the Hubble constant are kilometers per second per megaparsec. A kilometer and a megaparsec, there's a huge difference. And this is the scale of the difference. 1 megaparsec is about 3 with 21 zeros behind it, kilometers. And so 70 kilometers per second is nothing compared to a megaparsec.
Yeah. Mm-hmm. We Greek Aristotle in 4 BC, he taught that decay happened only on this planet and not in the universe. It can never change or decay. From the most recent discoveries of science, can the universe decay?
So the question was, can the universe decay? And I'm not quite sure what you mean by that. Like, what would constitute a decay?
Yeah, exactly. Or even just the most simple example of a shirt or something, can decay. Can the universe decay? The stars,
mm-hmm.
All that.
Yeah. So a shirt, if you just leave it sitting in a room for a very, very long time, is eventually going to sort of rot and unravel, right? And this, in one way, in a very abstract way, is an expression of what's called the second law of thermodynamics, which says that disorder always increases. And this happens on every scale. It's true that the universe's disorder is increasing over time. And so, in a very abstract way, yes, the universe is decaying. Although, I guess a little bit more precise way of putting that would be that the entropy of the universe is increasing with time.
Can I just make a comment to maybe put that in perspective for people? So the second law of thermodynamics, so everything tends to disorder. So the state of life actually requires energy to put us into the order that we are.
Mm-hmm. Yeah, that's exactly right. Right. So here's how the second law of thermodynamics, eventually is going to apply to the universe as a whole. So right now, most of the energy in the universe, and certainly the energy we use right now, comes from stars. And stars burn hydrogen. But there's a finite amount of hydrogen in the universe. So eventually, all of the hydrogen is going to run out, and we'll have no more star formation. And the existing stars are going to die because they're consuming hydrogen, and they also have a finite amount of hydrogen. So eventually, there's going to be no stars in the universe. And all of the stuff that's around is going to fall into black holes. Now, that's not going to happen on a short time scale. That's going to take much, much longer than the current age of the universe. But eventually, that's going to happen. Right, so at this point, the universe is full of black holes. And then the black holes are going to evaporate, because that's what black holes do. There's something called Hawking radiation, derived by Hawking. And I think this happens on a time scale of 10 to the 100 years. 10 to the 100 is called a Google for some reason. But yeah, so after 10 to the 100 years, there's going to be no stars, no planets, no gas, no black holes. The universe will be filled with photons from decayed, evaporated black holes. And that's the practical way in which the universe goes towards maximum entropy. A uniform, basically, soup of photons.
Is the theory that you just described inconsistent or consistent with the concept of an infinite universe?
It's fully consistent. Right, sorry. So is the concept I described consistent or inconsistent with an infinite universe? So it's fully consistent, because even though, so let's assume that the universe is infinite, well, our observable universe is still finite. And because the expansion of the universe is accelerating, there's a horizon beyond which we can never communicate. So something that's a certain distance away from us, we're never going to be able to send any signals to that thing. And that galaxy, that person, can never communicate with us in any way. So for all practical purposes, to us, the universe is finite, even if it's actually infinite.
My second question, that I have to clear up an assumption first here to make the question make sense. My assumption from what I've read is that gravity is a function of mass. Mm-hmm. More mass, the more gravity. Okay, if a black hole is a singularity, tiny, tiny little point, but it has all of that gravity, where's the mass that's causing that gravity to come from?
Yeah, so that's a question that nobody knows right now. Right, sorry. The question is, if you have a black hole, and we think all of the mass is in a singularity, in a point, then where does the gravity come from? Right, well, where is the mass? Right, so if you just follow the current theories naively and you derive what happens when things fall into a black hole, the theories tell you they end up in a point, right, called a singularity. But the thing is, our equations that we have right now break down under those conditions. We don't actually have a theory that can describe what gravity does on very small scales and very strong gravitational fields, which is what happens in the middle of a black hole. Now, people have been trying to come up with this theory for decades, because we know it has to exist, because something has to happen at the center of a black hole. But nobody has succeeded so far.
That's why they call it a singularity, because the computations don't work when you get down to that.
Essentially, yes. It's a theoretical point mass, but only theoretical.
Thank you.
Mm-hmm.
I'll leave you guys alone. When I ask my students about their favorite subject, raise your hand if you like social studies, no hands go up. Raise your hand if you like English, a few hands go up. When I ask about science, all hands go up, right? Science blows all the other subjects away, okay? At the age group that I teach was about 10 years old. Mm-hmm. But I've noticed
round about 7th or 8th grade, science in education drives off a cliff. Suddenly, they're just not interested in it anymore. So I was wondering if any of you encountered like a wall in your education where you were like, wow, maybe I'm not so interested in this anymore, and you had to overcome that. Did any of you encounter that, or what do you think causes this wall that kids hit around about 7th or 8th grade or whatever? Anybody?
Sure.
Poor Denise.
No, I like. It's fine. I like talking. I could talk for a long time. I think part of the answer. I should probably repeat the question. So the question is. It seems like very young elementary school children are overwhelmingly extremely interested in science, and then, interest seems to drop, in more middle school level. And so have any of us experienced, hitting a wall with our motivation in doing science? And what do we think about that decline? I would say, for me personally, I don't think that I ever really lost interest in science. But my theory as to why that happens maybe is possibly at least partially due to math. I think, because I think that that's about the level where science starts to involve a lot of math. And I think, sometimes kids maybe lose interest in math because they view it as, very dull, like, oh, I just got to do all of my multiplication tables and I got to do all of this stuff. And sometimes, because sometimes, people haven't been exposed to the joys of math, or, maybe I sound very corny saying that. I think math is really awesome, maybe more so even than my fellow astronomers. And sometimes, maybe kids don't realize all of the really, really cool things that you can do with math, like the fact that it, makes astronomy work and all of this. So I think, maybe part of the key to keeping kids interested in science is keeping them interested in math. Possibly. But I'm no expert in education, so grain of salt.
Yeah, so first of all, I think our teachers are doing a great job and they should be paid more. But to get to your point, I do think education plays a role. I think some of that is not necessarily teachers' fault, but the way science curricula are often set up, or you learn facts, you learn, the scientific method, which seems really step by step, right? First you come up with the hypothesis and then you test the hypothesis. I don't even know what the scientific method is because that's not really what science is. What science is a way of thinking. And math too. Math is also just a way of thinking about the world in a way that is logical and makes sense for the most part. But and science is, sometimes it's tedious, and I honestly, to answer the other part of your question, I hit the wall every day. Every day something comes up and I'm like, oh my God, why am I doing this? But I do it because it's really interesting. Like this, I think kids tend to lose that innate curiosity because they're told that science is a bunch of facts when it's not. It's the cool stuff. It's the stuff like space is cool. Things in space are cool. And it's really easy to lose that if you're inundated with this message that you need to just memorize a bunch of things or you need to pass this test. And I think that's part of where that comes from. Yeah.
Yeah, so as I mentioned earlier, I didn't like science as a kid. Actually, social studies is my favorite subject when I was little. And the reason why social studies is my favorite subject is because it was all about stories, right? It was all about like taking one thing and then connecting it to a million different other things. And I felt like there's a lot of creativity in being able to tell stories. And that's the one thing that I didn't get out of my science education when I was young, was that I always thought that science was sort of just following lots of procedures or, memorizing lots of facts. And I wasn't really interested in that. But eventually, once I sort of got to college and started taking college-level science classes, I realized that, people actually know almost nothing about science. Scientists know very little about how science works. And there's just this wide open universe that, you basically throw every tool that people have come up with over the last thousands of years at the problem to see, whether one of them will stick, to see whether this, slightly different angle of approaching the problem will help you make a little bit of progress. And I like that a lot. I like that sort of element of creativity in science. And I think that's one thing that's really missing from education at elementary school, middle school, and high school levels.
May I contribute something to that, please? Yeah, sure. Because that problem of how do you maintain an interest, how do you inspire an interest in students in science was addressed here at Caltech in the 60s. They found that the students were just bored with physics. They said, what are we going to do? So they asked a young new professor here by the name of Richard Feynman to come up with a new series of physics classes, which he did. They're now known worldwide as the Feynman lectures. But how did he do that? There's a long answer, but the short answer is he taught the pleasure of finding things out. That's one of his phrases. And the whole idea is that not that you have to memorize all these formulas or numbers or methods for doing things. It's that you find something that really fascinates you and then follow that. And that's what really needs to be taught if you want to really encourage people to study not just science, but anything. Develop an interest in it and learn more about it.
Right. Let's see.
Let's
Yeah.
Okay, so on the basis of being inspired, because I have to do only general ed, I can't take classes I want with physics and astronomy yet. But I'm usually inspired by the books I read, like Black Hole Wars and Leonard Susskind. I love that and reading that. And I just wanted to ask, do you have any recommendations on things that may have inspired you in that field of physics, astrophysics, astronomy?
I can answer that. So yeah, so yes, I'm going to repeat the question. Don't worry. Yeah. So the question is, do we have any recommendations on books that inspired us to pursue astronomy and physics? So a couple of books that really stick out in my mind as books that inspired me are number one, A Brief History of Time and the Universe in a Nutshell by Stephen Hawking. I read those books a number of years ago, and they really stuck with me, I think, as being, very good expositions to the study of cosmology. Another book that I really liked was actually not really about astronomy, but it was called, no, it wasn't really about astronomy, but it was called The Elegant Universe by Brian Greene. That was mostly about string theory, but yeah, for a popular audience. I would not be able to read a textbook on string theory. I have not taken enough classes for that. But yeah, so those are a couple of my personal favorite books for a general audience about physics and astronomy.
Yeah, so something I really liked is A Short History of Nearly Everything. Kind of forgot who the author was, but you can definitely Google the title. And it's not just about astronomy. It is about astronomy, but it's also about geology, biology, physics, I think a bit of math. And the good thing about that book is it tells stories. It tells the story of how we came to know the things we know. For example, right now we know the Earth is 4.6 billion years old. But how did we know that? Before, people thought it was a few thousand. So, it guides you through the centuries. Yes, by Bill Bryson. Yeah, so it guides you through the centuries. Yeah, A Short History of Nearly Everything. Yeah, it guides you through the centuries, discovery by discovery, and it gives you a holistic view of how we came to know all of these things.
Yeah, I definitely second the Brian Greene recommendation from Denise. Also, one of my favorite science-y books, this actually isn't about astronomy at all, when I was growing up, was a book by Douglas Hofstadter called Gödel, Escher, Bach. It's one of the best books I've ever read. Still, yeah. Gödel, Escher, Bach. Mm-hmm. Yeah.
that I like that's much more general physics is called First You Build a Cloud by Casey Cole, which I think was what really sparked my interest in physics in high school. I don't remember when I read it. It's a good book. It's much more general and it's not as technical. It doesn't delve into a lot of technical details, but it's a lot about, like, sometimes when I hit that wall, I read it and remember why I think that physics is cool. So we had a question from Fred?
Yeah, more specific with math. I know there's multiple equations out there. Is there one universal math equation or at least effort towards finding one where you can interchange constants and it's always consistent?
So the question is there one math equation that people are working on to describe all of the universe? So there's something called the Standard Model of Particle Physics, which I think captures as much as we can, but still misses a lot of really important things. So the Standard Model of Physics it's an equation that fits on a t-shirt. People sell it online if you want to look it up. Do I understand it? No. But in short, it contains three main parts, and those parts are the electromagnetic force, the weak nuclear force, and sometimes the strong nuclear force, which are three of the four fundamental forces in the universe. The fourth is gravity. I don't think anyone knows how to work gravity into there yet. So,
we have lots of ideas.
Yes.
We don't know if any of those ideas are right.
Yeah, so we don't know how to work gravity in there yet, but we have at least three of the four fundamental forces that more or less fit in an equation on a t-shirt. And it seems to hold pretty well with what particle physicists have found. So people working at places like CERN, where the Large Hadron Collider is located in Switzerland. For the most part, all of the observations that we've seen match pretty well with the predictions from this one equation. We had a question here? Did you have one? Nope. Okay. 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 Back there, yeah?
Yeah, so in astronomy and just viewing space, it seems like a perspective of like where the observation device, like the telescope is important. And like, for example, the Hubble telescope they put in orbit, and then most recently we learned about Gaia, they put that in space. Is it like a new, like what's the next location that they want to put a telescope that provides some sort of advantage that they haven't done yet?
So the question was, what is the next place that people are trying to put a telescope that might give it some advantage? So one upcoming telescope is called the James Webb Space Telescope, which will launch sometime. It was supposed to launch, when was it supposed to launch for the first time? 2016? 2007? Okay, all right, it was supposed to launch much earlier, but there have been various delays. The idea behind the James Webb Space Telescope is that it will be the next Hubble. It will be better because we will have taken all the things that we've learned since the launch of Hubble in the 90s, and we'll have included all of that into the James Webb Space Telescope. And it will also be able to look at different wavelengths. So it'll look at not just the visible wavelengths, which is mostly what Hubble looks at, but it'll also be able to extend even into the infrared. So part of the reason it's taken such a long time to launch is because in order for it to see into the infrared, we'll have to put it on the side of the Earth that's not near the sun, because otherwise the sun will just screw everything up because the sun emits a lot of infrared light. And this means that we won't be able to reach it. So unlike Hubble had a defect and we sent astronauts up to fix it. We won't be able to do that with this telescope, which is why everything has to be perfect the first time. Does anyone have anything else to add?
So one cool location to put a telescope is on the moon. Because if you're on the moon, you don't have an atmosphere. So you can you can take measurements at wavelengths that are blocked by the atmosphere of the Earth. So I think the Chinese government has a spacecraft on the moon right now that has a really tiny UV telescope. How tiny is 15 centimeters, so like this big. And I thought they were just doing this as a publicity stunt, just to prove that it's possible. Amazingly, they've actually published papers with observations taken by this tiny telescope. So yeah, if we ever get a moon base, which I'm hoping we do, the moon will be a great place. You can take observations not only in the UV, but basically in any wavelength, day or night, because there's no atmosphere to make the sky bright.
I want to know your guys' perception of interstellar.
So the question was, what was our perception of Interstellar? I loved it.
What you saw as an astronomer, you were able to see things that us as the normal citizen can't.
So when Interstellar came out, I was an undergraduate, and I went with basically my entire physics department to the local movie theater, and I was sitting next to the professor who taught me general relativity, and so I guess I'm not gonna worry about spoilers because it came out like 5 years ago or something. So there's this part where they're on this planet that is really close to a black hole, and time slows down by a huge amount, and this plays like a big role in the plot. And so the professor was like sitting there, and he was like, doing some calculations on his phone, and he was like, wait, this is too much slowing down of time. This is wrong. Like, yes. Yeah. So it's getting there. He was like, this planet would have to be within what's called the innermost stable circular orbit for a black hole, which is, as the name implies, as close as you can get to the black hole for something that can actually, stay on an orbit and not fall into the black hole. And it turns out that he was wrong, as Denise just said. And he realized this the next day because he assumed the black hole wasn't spinning. But if a black hole was spinning at the maximum allowed rate for a black hole to be spinning, and the planet was sitting at the innermost stable circular orbit, then you would get that exact time dilation. Yeah. Can't be equal to 1?
You can asymptotically approach 1.
Yeah, okay, yeah. Well, very close to that. Within the measurement error. I mean, they didn't specify the time dilation to like 10 digits or something.
Yeah, so out of departmental loyalty, I will say that, it's for the first like 2/3 of the movie, it's scientifically accurate because Kip Thorne worked on it, and Kip Thorne's a professor here. I hate the movie. I just don't like Matthew McConaughey's voice and his like attempt. Yes, it's terrible. I'm sorry. I don't like his weird affected southern attempt at a southern drawl. As somebody from North Carolina, I'm like personally offended by his attempt at that. Whatever. Okay, that's my opinion. Michael's turn.
Okay, I have an opinion on Interstellar that I think is funny. I think it's unfair to biologists. I don't think that it would be possible to I don't think that it would be easier to evacuate people from Earth and go to a planet orbiting a black hole somewhere through a wormhole that randomly exists for some reason than to cure a plant disease. I don't think we're giving the biologists enough credit.
Do you think that might be a possibility? Way out there?
Evacuating planet Earth to a new planet around a black hole? Well, not on the time scale where this movie is supposed to take place. Certainly not.
Yeah, so my approach to movies is exactly the opposite of his professors. I take the caveman's approach, which is like, ooh, pretty pictures, funny sounds, me likey. That's what I think about movies. I don't care if there's any science or it's scientifically accurate, just whatever. One of my favorite TV shows is Futurama. They try to be as absurd as possible, I think on purpose. They have giant whales floating in space.
Actually, I feel like I have a serious opinion to maybe sum this up. I think Interstellar would have been I think it would have been better if they hadn't tried to bill it as the most scientifically accurate movie ever made. I think we would all have had an easier time just enjoying it if they hadn't pitched it as, oh, this movie is totally hard science.
The Martian.
Yeah, no. It was a fun movie, though.
Yeah, that simulation of the black hole, by the way, was an actual simulation incorporating all of the physics that you would get around an actual black hole of those parameters. And so, that was my favorite part of the movie. That's why I liked it so much. It was just the beautiful visual.
I couldn't quite understand, but is the string theory involved when he was able to then go back on Earth in a different dimension and actually move physical objects
Okay, so that part, the thing about when he was in the black hole and was like, the fifth dimension is love, that is, yeah, that part was a bit sketchy, let's just say that. Yeah, that was entirely Hollywood.
To be fair to string theorists, a lot of what they do is presuming that there are a lot of dimensions that we can't see or perceive in any way. But yeah, okay, it's not, probably not love. But to be fair, like I think they took the seed of an idea that is actually in string theory and took a very hard left turn with it. Yeah, okay. So do we have any other questions?
Would you have liked The Martian if Matthew McConaughey was...
Oh, God. So the question was, would I have liked The Martian if Matthew McConaughey was not in it? I don't know, honestly. I went into The Martian wanting to like The Martian, I think, much more than I wanted to like Interstellar. But Matthew McConaughey might have killed it for me if he was in The Martian, because I really... It's the accent. It's the voice. Okay. All right. That's also a personal opinion. It's not affiliated with Caltech, whatever. Okay.
Any opinions expressed?
Yeah.
Beyond reflects the institute or whatever the legal line.
All right. Any other questions? If not, I don't know what time is it actually. Yeah. Thanks so much.